In this video, we discuss a light ray transitioning from a slow medium to a faster medium, and we derive a relation for the minimum angle causing total internal reflection. Finally, we work an example of total internal reflection. So when light changes from one medium to another, some percentage of the intensity is reflected and some is transmitted. So in this top picture, we have a ray inside this slower medium. It reaches the interface between two media, and the transmitted portion, that's the refracted portion that goes into the new medium, and it bends away from the normal because it went into a faster medium. At the same time, some percentage of the intensity is reflected, and that would follow the law of reflection, where the reflected angle is equal to the incident angle. So we notice when light moves from a slow medium to a fast medium, the transmitted ray, that is the refracted ray, is going to bend farther away from the normal. And in the second picture, we're doing a little experiment. We're letting the incident angle become bigger and bigger and bigger. And of course, as a result, the refracted ray is at a bigger and bigger and bigger angle. But the fact that it bends away from the normal means that we should be able to get to some critical angle here, where the refracted ray actually has an angle of 90 degrees. Well, what happens when we hit 90 degrees? At 90 degrees, the ray is no longer exiting the material at all, and there is no transition to the faster medium, and suddenly 100% of the light intensity is reflected back into the material. So it all goes into the reflected ray. So when light is hitting at a shallow enough angle at an interface from a slow to fast medium, you can get to this cut point where suddenly all the intensity is reflected and none of it is transmitted, and this is called total internal reflection. So in our example, we want to get the minimum incident angle for total internal reflection when a ray passes from crown glass into air. And we simply apply Snell's law to solve this thing. I'm going to use a 1 to index the glass and a 2 to index the air. And I'm trying to find the incident angle as that ray inside the glass hits the interface with the air. Again, air has an approximate index of refraction of 1, so that my refracted angle is 90 degrees. And then any incident angle bigger than that is going to give you total internal reflection. Well, the sine of 90 is 1. Solving for theta incident, I divide by 1.52 and invert the sine function, and I have the inverse sine of 1 over 1.52. And I get an incident angle of 41.1 degrees, so anything bigger than that, and you're going to have total internal reflection. No light escapes the material at angles this shallow. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.